Hello everyone, welcome to the Chemistry channel. So today begins our series of lectures on the periodic table. So in this lecture we're going to be discussing atomic number, atomic mass, and atomic weight, and the difference between them. So let's begin. So remember from the first lecture that atoms are made up of subatomic particles, and one of these subatomic particles is the proton. So the number of protons in an atom determines its identity. So the number of protons in an atom determines its identity. So what is this number of protons that we are talking about? It actually has a specific name: atomic number. Atomic number is the number of protons in an atom. So atomic number is the number of protons in an atom, okay? So the atomic number is what determines the identity of an atom. So for example, if you have an atom that has 6 protons, an atomic number of 6, that atom will always be carbon. So if you were to look, let's actually make that a little bit nicer. So if you were to look at the periodic table of elements, you'd see a number on top of each element. And this number on the top is the atomic number. So every single carbon atom in the universe has 6 protons. If an atom has 1 proton, that atom will always be hydrogen. If it has 2, it will be helium, etc. So it's the number of protons that determines the overall identity of the atom. However, atoms can also be classified in another way, and this other way is through their atomic mass. So the atomic mass of something is the exact mass of an atom. So I'm going to emphasize the exact mass. It's exactly how much an atom weighs. And atomic mass is often expressed in atomic mass units. So AMU. And you may remember from my first lecture that 1 atomic mass unit is equal to 1.66 times 10, it's actually approximately equal to 1.66 times 10 to the negative 24th grams. So it's actually a very, very tiny amount. So the atomic mass of an atom, so I'm just going to symbolize it as AM, is equal to the number of protons times 1 AMU plus the number of neutrons times 1 AMU. So the atomic mass is basically equal to the number of protons added to the number of neutrons. And we multiply each one by 1 AMU because both protons and neutrons are approximately equal to 1 atomic mass unit. Okay? So let's take a look at 2 forms of carbon. So believe it or not, there's actually 2 main forms of carbon that you need to be worried about. So you'll see these 2 forms of carbon expressed like this. So the 6 At the bottom is the atomic number. Every single carbon atom in the universe has 6 protons, so its atomic number will always be 6. However, these two carbon atoms differ at the number at the top. So this number at the top is the atomic mass. So if their atomic masses differ, but their atomic numbers are the same, by what species are these two forms differentiated at? In other words, do they have different amount of neutrons, different amount of protons? What do you think? Well, the answer is that these two forms of carbon have a different amount of neutrons. Carbon-12 has 6 neutrons because the atomic mass, which is 12, is equal to 6 protons plus the amount of neutrons. And if you solve for x, you get 6, so 6 neutrons. However, for carbon-13, you have 13 is equal to 6 protons plus x amount of neutrons, and when you solve for x, you get 7. So they only differ by the amount of neutrons. That's why these two forms of carbons are called isotopes. So let's now define an isotope. Isotope. So the isotopes are atoms with the same atomic number but different atomic masses. And this is because they have a different number of neutrons. So they have different amounts of neutrons when compared to each other. Okay? All right, so let's take a look at what carbon looks like on the periodic table. So if you were to look at carbon on the periodic table, you'd see this little box, and then carbon, this letter C in the middle standing for carbon. You'd see a 6 at the top, where the 6 is the atomic number. However, at the bottom, you'd see 12.01 around there. So what is this 12.01? This 12.01 is not equal to either of the atomic masses here. So what is going on? Well, the periodic table does not report atomic masses. The periodic table, this is periodic table, reports atomic weight. The periodic table does not express atomic mass. It only reports atomic weight. So what is atomic weight? I'm going to symbolize it like this. Well, atomic weight is defined as the weighted average of all naturally occurring isotopes. So it's the weighted average of all naturally occurring isotopes' atomic masses. Okay, so what does this mean? Well, you can express this as a formula. So atomic weight is equal to the sum of each isotope's mass and each isotope's mass is multiplied by the fractional abundancy, which I will label as Fi. So the fractional abundancy is basically how common a particular isotope is in nature. Now, you can also express fractional abundancy as natural abundancy when you multiply it by 100%. And this will give you the natural abundancy. So these are the two equations that you need to know for atomic weight. So I think the best way to explain this is through our carbon example. So let's do that. So let's change our color to purple. So carbon has two main isotopes that we have to worry about in Gen Chem. So carbon-12 and carbon-13. So carbon-12 has a natural abundancy of around 99%, and carbon-13 has a natural abundancy of around 1%. So this means that 99% of all carbon-12 found in nature is, this means that 99% of all carbon found in nature is carbon-12. So carbon-12 makes up 99% of the carbon found in nature. Around 1% of carbon found in nature is carbon-13. So that's what these two numbers are saying. So let's find the atomic weight of carbon. So the atomic weight of carbon would be equal to 12 AMU for the carbon-12 isotope times its natural abundancy, or its fractional abundancy, 0.99, plus 13 AMU times its fractional abundancy of 0.01. And when you plug all this in, you would get around 12.01 atomic mass units. If you want to use the appropriate number of sig figs in this case, you would get atomic weight is equal to around 12, because we have two. But we're going to use this one in this case, because this is the one that you would see on the periodic table. And of course, if you got this on a test question, your exam would give you a much more precise measurement. So if you had to calculate this, your value would be around this with the correct number of sig figs. Okay? So that's all the concepts for today. So let's get into one practice problem for today. Only one, because we didn't really go over too much today. And it's a little bit hard. It's a very difficult problem. So this is an atomic weight problem. So you're going to try to find you're going to use the atomic weight to find something. So let's say that you have a hypothetical atom X. Now this hypothetical atom X has an atomic weight equal to 100.000 atomic mass units, okay? So 100.000 atomic mass units. And it has two naturally occurring isotopes. The first naturally occurring isotope weighs 95.000 AMU, and the second one weighs 103.000 AMU. What I want you to do is find the natural abundancies of each isotope for this hypothetical atom. So find the natural abundancies. So I encourage you to pause the video and try it for yourself. Okay, so hopefully you paused the video. So let's tackle this problem. All right, so let's just choose a different color here. Let's use blue. Okay, so let's set up our equation. So atomic weight in this case is equal to 100.000 AMU. And this will be equal to the fractional abundancy of isotope 1 times the atomic mass of isotope 1 plus the fractional abundancy of isotope 2 times the atomic mass of isotope 2. So let's just put in the numbers here. So let's just erase that. Okay, so 100.000 AMU is equal to the fractional abundance of isotope 1 times 95.000 AMU plus the fractional abundance of isotope 2 times 90, not 95, it's 103. So let's change that. Times 103.000 AMU. So the problem here is that we have two unknowns and only one equation. So we have to come up with another equation. So since we have two isotopes with two different natural abundances, the sum of each fractional abundancy, the sum of the two fractional abundances for this hypothetical atom will add up to 1. So F1 plus F2 will equal 1. So in order to solve the equation above, all we have to do is arbitrarily solve for either F1 or F2. So let's do F2. So F2 is equal to 1 minus F1. So now what we're going to do is plug this in to the equation above. So we have 100.000 AMU is equal to F95.000 AMU times F1 plus 100 and, what was it, 103.000 AMU times 1 minus F1. So now we just distribute. So let's just rewrite it like this. Minus 103.000 AMU times F1. So let's subtract 103 from both sides. Like this, which would give you a negative 3.000 AMU, like that. And then you would have 95.000 AMU times F1 minus 103.000 AMU F1. So then we just can combine these two terms together, which would give you minus 8.000 AMU F1. And when you solve for F1 by dividing the negative 8, you should come up with a value equal to, so 3 divided by 8, 3 divided by 8 would give you a value of 0.375. Okay? 0.375. And in order to find F2, you just do 1 equals F1 plus F2. 1 minus F1 will equal F2. And F2 will equal 0.625. So those are the fractional abundances. And if you want to turn them into the natural abundances, you just multiply by 100%. And this would give you 62.5% and then 37.5%. And now let's make sure that both of these correspond to the right values. So 95 times 0.375 plus 0.625 times 103 gives you exactly 100. So once you plug these two back in here, you'll see that those two values work. So that is your answer. Let's just make sure, actually, let's do a little sig fig exercise. Let's make sure that we have the correct number of sig figs. So we have 6 here, 5 here, and 6. When you subtract the 103 from the 100, you come up with 4 sig figs because you conserve those zeros after the decimal. And then when you put these two together, you get the -8, you conserve those zeros. So therefore, when you plug that in to your calculator, you can, when you divide 8 from 3, so we have 3.000, so that is 4 sig figs. And then you have 8.00, you have 4 sig figs. You should come up with a value of 0.3750. So you should actually have 4 sig figs in your measurement, so it's even more precise than I actually showed. So therefore, let's correct that for our correct number of sig figs. So instead of 37.5, it's 37.50 and 62.50%. Okay? And that's it. Let's put the 0 here. So that's just taking into account sig figs. So that's it for the video today. I hope I helped you. And if you have any questions or comments, put them in the comments section. Feel free to do that. And I will see you in the next video when we continue talking about properties of the periodic table. So I thank you all and have a good day.